Thanks everyone for coming to the talk. Video conferencing has now become a major tool for our meetings, especially during the pandemic when everyone is working from home. However, we all have this experience. You're in the middle of a meeting and the video just freezes, simply because you don't have enough bandwidth. To resolve this, what we propose is a new framework that consumes only 1/10 the bandwidth of H.264. Here we show comparison. Using the same bandwidth, our video is much sharper than H.264 results, which contains a lot of artifacts. We present a talking head model that can do video reconstruction, head rotation, and motion transfer, all at the same time. For video reconstruction, instead of transmitting the full RGB frame, we only transmit the head pose and expressions. Here we show a side-by-side comparison where we gradually reduce the bitrate for H.264 and H.265 from 12x of ours to 2x. As you can see, the videos gradually become blurrier, while ours still remain sharp. In addition to reconstruction, we can also generate free view videos where we change the head pose. Given a single view image, we can easily generate the same person under different poses. This enables us to generate free view videos to create the often missed eye contact in modern video conferencing. We show side-by-side comparisons with two face frontalization methods. Only ours can reproduce the identity faithfully. Finally, our model can also do motion transfer of different identities. Here's a comparison with the existing one-shot methods. Only ours can realistically reproduce the motions. Next, let's talk about some technical details. On a very high level, our network takes the source and driving images as input and generates two sets of 3D key points. These key points are used to predict a flow field, which is used to warp the source features extracted from the source image. The warped feature is then passed to a generator to output the final image. The most novel part is how do we estimate the source and driving key points unsupervisedly. We decouple the estimation process into an identity branch and a pose branch. In the identity branch, we use the detector to estimate canonical key points. Note that this only encodes the identity information and is independent of poses and expressions. Next, in the pose branch, we estimate the head rotation, translation, and expressions. These parameters are then used to transform the canonical key points to obtain the source key points. Similarly, for the driving image, we apply the pose branch to get the pose information. Since the identity is the same, we reuse the canonical key points from the source image and transform them to get the driving key points. The two estimators share weights in our network. Here's a visualization if we use the intermediate key points to synthesize the outputs. We first predict a canonical view from canonical key points. Then we use these parameters to apply rotation, translation, and expression information sequentially to obtain the final image. This leads to a compact representation for video streaming. We can now decompose a video into a canonical view, which is fixed throughout the video, and the varying parts are only these parameters, the head pose and expressions, so transmitting them requires much lower bandwidth. Our model also has some other additional applications. We can animate portrait paintings, for example, using the photos generated by StyleGAN. Combining it with audio to face, we can generate face motions given only voice as input. By changing the pupil key point positions during synthesis, we can easily manipulate the gaze directions as shown here. Thank you. Please find more details on our website.